In exercise 4.3.7, we are given theta equal to 4, and then two random variables. Y is a random variable taking values 3 and 7, both with probability 1/2. These are both 1/2. And x is a random variable that takes the value, or it's an exponential random variable with parameter y, conditional on y being y, capital Y, the random variable being the value y. Now the key takeaway of this exercise is it's important to know how to write a story like this for this conditional random variables into a mathematical formulation of these random variables. The key solving ingredient will be a previous question, 4.3.3, and the R equation, the equation for the adjustment coefficient. Now let's start by, we are asked to show that you have to determine you have to determine R, so determine this adjustment coefficient and check that if R equals 2, then what happens to theta? We can start by asking a question, how does x, the random variable, look like? In other words, how do we represent it? Now, notice that y takes the value 3 and 7 with parameter 1/2, and x takes an exponential random variable based on these values. So x can be two things. It's either exponential with parameter 3 or exponential with parameter 7. So we can already split x into two parts. So let's say x1 and x2, where x1 is exponential with parameter 3 and x2 is exponential with parameter 7. Now we just have to determine when does the one happen and when does the other happen. So this is the case if y is 3, and this is the case if y is 7. And these are both with probability 1/2, right? So this is with p is 1/2, and this is also with p is 1/2. So we can actually represent this with a Bernoulli random variable, as we have seen before in the book. So we say I is Bernoulli. Is I Bernoulli with parameter 1/2. And then we see that indeed if this Bernoulli random variable equals 1, then this one happens. Then we are here. I is 1. So then y takes the value 3, and this happens with probability 1/2. And then x1 is equal to the exponential distribution. And similarly, if I is 0, then this one happens. In any case, we have to keep in mind that these random variables are all independent. So I, x1, x2 are independent. They do not influence each other. Alright, so now we have a formulation for x, and from there we can actually write down, using this independence property, the density function of x. So the density of x, and you can, to see the C, equation 2.11 in Mart. And it's given by the sum. So this 1/2 comes from the Bernoulli, from the Bernoulli random variable, and it's the sum of our exponential random variables. And this equals, in the case of x1, it's 3e to the power minus 3x, and in the other case it's 7. And actually this is px in question 4.3.3. And why is that important? Well, in exercise 4.3.3 we actually derived what the value of r is, of the adjustment coefficient. So in Q 4.3.3 we saw r equals 1. This was the solution. Now the second part of the exercise, so we are done with the first part, and the second part says that now if r equals 2, do we have that theta equals, or theta is, let's say, smaller or larger than 0.4. So we started out with theta being equal to 0.4, that's our assumption. And the question is, if we change r, what happens to this theta? Well, we know by definition that theta is, or r satisfies its equation. So let's call it, I call it the r equation, the adjustment coefficient equation, which states that 1 plus theta times mu1 times r is equal to mx r, where mu1 is the expectation of the claim, so it's expectation of x, and mx of, let's say, t, the moment generating function of x. We also derived it in question 4.3.3, and it's given by a mixture of exponential moment generating function with parameters 3 and 7, given by right here. Alright, so this is question 4.3.3. And doing some rearranging, we have, okay, that this equation is actually equal to the moment generating function plugged in r minus 1 over mu1 times r minus 1. And then if we plug in r is 2 and the moment generating function, and using that mu1 is actually, let's say, put it here, was equal to 5 over 21. Now plugging this all in, it gives us that theta is equal to, write down one more step. So this is the moment generating function plugged in. This should be a 5, and then we divide over 5 over 21 times 2 minus 1, and this gives us 1.52. So this is definitely bigger than 0.4, which answers the second part of the question. So it's back to the takeaway. It is important to know how to write this story, or these two random variables x and y, and to make sure you are able to realize how we can then obtain an expression for this random variable.